This is AP Calculus AB. We are on notes 11-1, area under two curves. Our objective today is to find the area under two different functions. All right, so let's dive in with an example. Example 1, find an area of the region bounded by the function sine of x in the first quadrant of the interval between 0 and 4 shown in the graph below. And just to make sure that we understand the question, I'm in the first quadrant, which means I have to be in the top right area. So this piece down here, I don't care about. I'm simply asking for the area that fits in that curve right there. So while I am allowed to use a calculator on this one, you don't actually need to know one. I just want to show you some tools that you can use on the calculator if you want to use it. So the general idea here is I'm just finding that area, therefore I'm taking the integral of that function. So what I need to do is I need to say, okay, the integral of sine of x, and then dx, and that's basically what I need to do. Okay, I need to have the correct bounds on this thing. So I know that I'm starting here at 0, and I'm ending here a little bit after 3. And if you know your trig pretty well, you'll know that this value is pi. If you didn't know that, there are some things that might help you. First, let's review the trigonometry. If you have a unit circle and you go 180 degrees, or if you go pi radians over here to pi, the y coordinate right here is 0. I didn't go up or down. So if the y coordinate is 0, sine of pi is also 0. Therefore, it has a height of 0. Another way to determine this is if you go to your calculator and you go to your y equals and graph sine of x. I have the window a little bit less than 0 and a little bit more than 4. And when I graph this thing, you can see it does have the same graph. And I do a second trace to do a calculation. I'm going to do a 0, so I'm going to hit 2. And then I'm going to say my left boundary is 3. My right boundary is 4. And you can see, oh yes, it's 3.14159. It goes on forever and ever. That's pi. Okay, so I've triple verified it has an end boundary of pi. And again, I need to do this, and I have a calculator. It says I'm allowed to use a calculator, but I don't need to use a calculator because I want to just show off my math prowess. This is equal to, well, the antiderivative of sine. Anti-same means change the sign to a negative, and it's always flip-flop between a sine into a cosine. So it's going to be negative cosine of x, and then evaluation bar from 0 to pi. And then this thing is going to be equal to, I'm going to pull the negative out and then not worry about it until the very end. So this negative, it's kind of hard to see, come on, move over. This negative and this negative are the same negative, and I'm just going to work on the cosine of x inside the parentheses here. So it's going to be cosine of pi first minus cosine of the other bound, 0. All right, so cosine of pi, I happen to know on the unit circle that pi is located right here, and cosine is talking about the x coordinate. So how far left or right did I move? I moved left 1. This is negative 1. Okay, and what about this cosine of 0 business? So cosine of 0, that was negative 1. Cosine of 0 lives right here, which is to the right, which is right 1. This is a positive 1. Cosine of 0 turns into a 1, which means if I end the parentheses here, this entire thing evaluates to a negative 1 minus that 1, or a negative 2. Unfortunately for us, we also have this negative on the outside that we need to deal with, which means my final answer here is going to be 2. That is the final answer, but I want to verify this with the calculator since I have the ability to use a calculator. So if I come here in second mode out of this, and I do math 9 to do an integral between 0 and pi. Again, pi is second and then to the power of. And then I'm going to type in sine of x. I get 2. So I've verified this both with pencil and with a calculator that this is 2. So this is just in general. To find the area between the curve and the x-axis, you're taking the definite integral of the function with the correct bounds. And that's generally the first piece of my objective. Can you find the area under different functions? We did it under 1. If it's under one function, you just take one definite integral. If it's under 2 different functions, you probably guessed, it's 2 different definite integrals. So to see that, let's look at example 2, and it looks like I have some stuff there. So in example 2, it says, let R be this shaded region down here in the first quadrant shown in the figure below. The region R is bounded by the x-axis, it's bounded by the graphs of f of x, and it's bounded by the graph of g of x to make our shape there. And it tells you what those functions are. It tells us what the function way down there, double verified. We need to find the area. So to find the area, we're using this knowledge that the area between the curve and the x-axis, we just take the definite integral. Well, there's a problem here, is right here, this area is in between. You can see I'm bouncing between the curve, the x-axis, the curve, the x-axis, the curve, the x-axis, and all of a sudden, a different function. I was bouncing between f of x, and then all of a sudden I switched to bound the g of x. So really, what I need to do here is I need to cut this in half. I'm going to draw this vertical line here, which is in the wrong spot. I'm going to move this right there. This spot, I don't know what x coordinate this is at, but I'm going to cut this in half so that I have one integral right there, because that'll be the integral of tan of x, because I know how to do the area underneath a curve and between the x-axis. I just take the integral of this thing right there, and that'll give me this area, and then I'll do the integral of this thing right here, and that'll give me that area. Done and done. Technically, I don't need to do that because this is a triangle, and I happen to know that, well, maybe, I don't know what that height is over here, but triangles typically you can do just by hand. So, if there are two different curves, then there are two different integrals. The problem is I don't know what the bounds of those integrals are. So let me set up the integrals, and I'm going to come back and find u. So first I have the integral from, it looks like 0 here, right? So from 0 to, I'm going to leave you blank for now. And that's going to be of our first function, which is tangent of x. Technically dx. Did I put a dx over here? I technically did put a dx. Good job, Mr. Sindel. And then I'm going to add that with another integral, and that's going to be from this this x coordinate that I don't know, I'm going to leave blank, to this 2. So this 2 is going to come up here, and we're going to say to 2 of this other function, which is 2 minus x, that entire thing, dx. Okay, so this is all set up. The only thing that I'm missing is that bound here. So how do I find that? Using a calculator, right? This would be kind of hard to do without a calculator since it is the trig value. So let's pull up a calculator here, throw it on the left, make it small. All right. So what I'm going to do is I'm going to go to my y equals button. Let's clear this out and type in tangent of x. And then down here, we're going to type in 2 minus x. We can graph both of these. And we can see that the bounds of our graph are going to be about from 0 to 2 should be plenty. So 0 to 2. I'm going to hit zoom 0. And that did not work. Did I type in something wrong? Tangent of x. Oh, I see. This tangent of x is going to repeat after pi over 2, which is right here. It's going to go to infinity. So maybe that's a bad idea. Let me go back to my window. And look at that y minimum. Let's change that y minimum to 0. So let's clear this out and put in 0. Come down here to this y max. Let's clear that out and put 2. And that's what the graph is showing over here anyway. So that works. And then we'll graph that. Okay, that looks like the thing that I'm looking for. So let's clear stuff out of here. So what I'm looking for is that intersection of the blue and the red line. So to find that, I'm going to hit second trace to do a calculation of an intersect. So it's option 5. So I hit intersect, and the left bound is going to be 0.5. The right bound is going to be 1.5. I think that's going to be a little bit different on your calculators. If I remember correctly, the TI-84CE, it asks you which function. You just hit enter and hit enter again, and then you have to estimate. It's a little bit different. Just follow the prompts. Either way, you should get something that says this bound right here. I'm going to erase the question mark and say the bound is actually, the x-coordinate is 0.854. 854, if I'm rounding correctly. It was 8535, but I rounded the 3 into a 4. So I know it's 0.854, so I'm going to come up here and say it's 0.854. Come over here and say 0.854. And does that make sense with the graph? Just making sure. Okay, so it's a little bit to the left of the 1, so that does make sense. Okay, let's go ahead and plug these things into our calculator and figure out what we get. So I'm going to do math 9 to do an integral between 0 and 0.8. Oh, that's not 8. 0.854 of tangent of x. So tangent of x. And we get 0.854. I'm like, that is a gigantic small value. It should be positive. So I'm going to hit second enter. I'm going to come over here, and right before the 8, I'm going to do an insert. So second insert, and then 0.854. And there we go. That seems much more reasonable. And it was 0.420, so that's why I put 2 decimal places. So it's, I think so, right? So let me check my mode. I have automatic rounding to 3 decimals. So this is going to be 0.420 plus that integral. So I'm going to do that integral now. It's going to be math 9, integral between 0.854, the point was actually entered correctly, to 2 of 2 minus x, and we get 0.657. Excellent. And then we can just add those together. So we can say, add that with 0.420, and we get our final answer of 1.077. That was a terrible block. Let me try to do that again. Nice. All right. Let's try another, shall we? Oh, this one, I need to talk about this. This is going to be in our speed sheet. Whenever we have the area under two different curves, and I'll give you some generic picture like this on the speed sheet, you always are going to do the integral of the left plus the integral, that's not an integral, plus the integral of the right. And that's kind of everything that you need, although it would also be nice to know that if you have an integral from A to, let's call it C, and it's broken up, and we'll say that is breaking over point B, so I have A, B, and then C. The way that this integral works, you go from A to B, and then from B to C. The main thing here is that these two numbers are the same number. They're talking about that 0.854. That's where they got glued together. It's kind of like that old suspect point, right? These B's had to be the same point because that's the end of this integral, and it's the beginning of this integral, right? All right, so let's do another example. So this one, I don't know if there's text here. This one, we know that we do not have a calculator, which means this calculator go bye-bye. All right, example 3. Let R be the region in the first quadrant shown in the figure below. It's pretty clear that we're talking about that thing down there. The region R is bounded by the x-axis and the graphs of x-axis, the graphs of x squared, and the graph of 6 minus x. It's clearly this thing right here. Find the area of R without a calculator. So again, I only know how to find the area between a curve and the x-axis. So right there, it looks like it might line up exactly at 2, but I need to verify that. We need to find where to cut that off. So I'm going to guess here it's 2. Let me draw my vertical line. It's probably right there. Good job, Mr. Snell. Let's verify that's actually the bound. Let's see what happens when I put this equation on top of that equation. When I set this number equal to that number to find where they intersect. That's what you do to find intersection. You set them equal to each other. You say, okay, so to verify intersection, you wouldn't actually write this on the real test, but I'm just taking notes. I'm going to set them equal to each other. I'm going to say x squared. I'm going to set that equal to 6 minus x. Well, oh no, how do I do this? It's a quadratic. Let's move everything over to the x squared side and see what happens. It's going to be x squared plus x minus 6 is equal to 0. And then I should be able to factor this thing. I can say that this is the quantity of x. Well, what two things multiply to 6? 1 and 6 doesn't help. 2 and 3 do help because 2 and 3 will somehow get to a 1. If I do plus 3 and minus 2, that'll get me to a 1, and therefore our answers are going to be negative 3 and positive 2. Again, using that zero product property. So these two x coordinates, this one doesn't show up. It's way out over here, which actually kind of makes sense because this is going to come up again and eventually intersect over here, which is that negative 3, which I don't care about for this problem. This one is on the problem, and it's the one that I guessed. It is 2. So I did verify the intersection, check, give myself the gold star. Now let's go ahead and do the actual piece that I was talking about. I need to do the integral of the left. So the integral of the left is going to be the integral of x squared, and I know my bounds now are between 0 and 2. I'll put a dx because I'm being super formal about this. And then I'm going to add the integral of my next piece, which is going to be 6 minus x, that entire quantity dx. And the bounds now are between 2 and 6, again, between 2 and 6. Okay, I have everything set up. I did integral of the left, integral of the right. Now I need to do this without a calculator. So I'm going to go ahead and pause for a second because this thing is way easier than it might seem, because this, as I said in the last problem, is just a triangle, and it's a triangle that has very nice dimensions. If I were to annotate this triangle and say, well, this length right here is just 4, and this length right here is also 4. Don't be fooled, it's not 6, it's actually 1, 2, 3, 4 units. So this technically makes a 4 by 4 square, which is 16, but it's a triangle, which is half of the square. Therefore, that triangle has an area of 8. So I'm going to cross this out and say this is really an 8. The only thing I really need to do is to find that integral of the x squared. And sometimes this is still a hard function to do. I just happen to show a shortcut in this one. This is the only thing I really need to do now. So how do I do this? Let's dive in. We go, we're going to check. Is there a tax person? Is there a tax man waiting? No, it's just x, right? The antiderivative, or the derivative of x is 1, so I am allowed to just bypass paying the tax person. And let's do that. So I'm going to go up a power, up to the power of 3, divide down by 3, and then it's going to be evaluation bar between 0 and 2. All right, so let's expand this a little bit. I'm going to ignore this 8 for a second. So if I expand this, this is going to be 2 cubed over 3 minus 0 cubed over 3. And it's kind of silly to write the 0 cubed over 3 when I plug in the 0, because 0 cubed over 3 is 0 to the power of 3 is 0, and then 0 divided by 3 is 0. This whole thing is just 0, which means this whole thing I just kind of cross out and say it's just 0. Okay, so I really only need to worry about 2 cubed over 3, which is the same thing as 8 over 3. And 8 over 3, do I want to keep it decimals, fractions? Let's just do decimals. I'm just feeling decimals right now. That's the same thing as 6 over 3 plus 2 over 3, which is the same thing as 2.667, rounding to 3 decimal places because I know 2/3 is 0.6 repeating. And then I need, okay, don't forget, here's the 8. 8 is going to come down here too, so let's go ahead and say plus that original 8, and I'll make a note here. This is from the, well, that arrow didn't point to the correct number. This is from the triangle. If I add these two together, this adds up to 10.667 for our final answer. Excellent. Well, again, I want to make sure that we come back to our objective. Were you able to now understand how to find the area under 2 different functions by cutting them into pieces and doing the left integral plus the right integral on a fist of 5? Hopefully, you're giving me high numbers here. That concludes the notes for AP Calculus AB Notes 11-1, Area Under 2 Curves. Thanks for watching.